how ancient Egyptians predicted the Nile flood every year. Without a single instrument every summer for roughly 3,000 years, the same event determined whether Egypt would eat that year. And Egyptian priests could name the date it would begin before it happened, sometimes to within a day or two, without a barometer, a satellite, or any instrument capable of measuring rainfall 1,000 miles upstream. Their method was almost absurdly simple. They watched the eastern horizon just before sunrise for a single star to reappear after weeks of invisibility. When it did, the flood that fed Egypt's entire civilization was, with remarkable consistency, only days away. That star was Sopdet, known today as Sirius, and its reappearance became so reliable a predictor that Egyptians built their entire civil calendar around it. What none of them ever managed to explain, despite 3,000 years of careful observation and a religion built substantially around the flood itself, was why the water actually rose at all. The star told them when. It never told them why. That second question would not get a real answer until long after the pharaohs. Their temples and their priesthood had all disappeared. For 3,000 years, an entire civilization built its economy, its religion, and its calendar around a natural event whose actual cause remained, from the Egyptian point of view, a complete and permanent mystery, solved not by better observation of the sky, but by a discovery made nearly 2,000 miles to the south, in a country most Egyptians never knew existed. Why this mattered. Egypt's entire civilization existed because of a geographic accident. Outside the narrow ribbon of the Nile Valley and its delta, the land on either side is desert, arid enough that unaided agriculture is effectively impossible. The 5th century BCE Greek historian Herodotus, visiting Egypt and observing exactly how completely its farmland depended on the river, coined the description that has stuck ever since. Egypt, he wrote, was the gift of the Nile. Each summer, the river rose over its banks and spread across the floodplain, depositing a fresh layer of nutrient-rich silt carried down from far upstream. And that annual deposit, rather than any fertilizer or crop rotation technique, was what kept Egyptian soil productive across thousands of years of continuous farming, without the kind of exhaustion that ended other ancient agricultural societies. The flood's arrival was not a gentle, gradual event. Water levels could rise several meters within weeks, and the entire agricultural calendar, planting, harvesting, tax assessment, temple festivals, was organized around 3 distinct seasons defined by the river's behavior. Akhet, the inundation itself; Pere, the growing season once the water receded; and Shemu, the harvest before the cycle began again. Knowing exactly when Akhet would begin was not a matter of curiosity. Villages needed time to move livestock to higher ground, secure grain stores, and prepare canals and basins to direct the incoming water efficiently rather than let it flood unpredictably. Work that in many regions relied on an extensive network of earthen basins and feeder canals, maintained through seasonal corvée labor, specifically designed to trap and hold floodwater across the widest possible stretch of farmland, rather than let the Nile's surge simply drain back into its main channel unused. A late warning, or no warning at all, risked losing both property and the harvest that fed the country for the following year. Even at its most productive, cultivable land in Egypt has never amounted to more than a small fraction of the country's total territory, generally estimated at well under 10%, concentrated entirely within reach of the river's annual reach. Every other consideration in Egyptian statecraft, from where cities could be built to how taxes were assessed, ultimately traced back to that narrow, flood-dependent strip of usable ground. The Egyptian year's three-season structure gave the flood's timing an outsized place in everyday planning that modern agricultural calendars. Built around gradual, predictable weather patterns, rarely require Akhet, the inundation season, typically ran from roughly mid-June through late September, during which most farmland sat underwater and agricultural labor shifted almost entirely toward canal maintenance, basin repair, and, according to some scholarly reconstructions, the large-scale state construction projects, including monument and pyramid building, that could productively absorb a rural labor force with no fields left to work. Hooray, the growing season followed as the floodwaters receded and exposed newly silted soil ready for planting. Shemu, the harvest and low water season, closed the cycle before Akhet began again the following summer. Each season's start and end were defined entirely by the river's behavior rather than a fixed number of days, which is precisely why an accurate, standardized way of anticipating Akhet's opening mattered so much to a government trying to coordinate labor and food production across an entire kingdom. The star that never lied. The solution. Egyptian priest astronomers arrived at relied entirely on a quirk of celestial mechanics available to anyone willing to watch the sky consistently. Sirius, the brightest star visible from Earth, disappears from the night sky for roughly 70 days each year as Earth's orbit carries the sun between Earth and the star's position. When Sirius finally becomes visible again, it does so first as a brief, faint point low on the eastern horizon in the minutes just before sunrise, an event astronomers call a heliacal rising. Egyptian priests, observing from fixed vantage points at temples, including those at Memphis and Heliopolis, track this reappearance year after year and notice something civilization-defining. Sopdet's heliacal rising consistently preceded the Nile's flood by only a matter of days, typically falling in the second half of June by the modern calendar. The correlation held with enough reliability, generation after generation, that priests could use it as a genuine early warning system. There was no mechanical instrument involved, no calibrated device, nothing beyond disciplined naked eye observation repeated at the same location at the same time of year, which makes the accuracy of the resulting prediction genuinely remarkable by the standards of any pre-modern society. Temple astronomer priests, sometimes titled hour watchers, maintained star charts recording the risings of Sopdet and other reference stars across successive reigns, building an observational record that let each generation of priests check their own reading against decades of prior data rather than relying on a single year's observation alone. Consistency of location mattered as much as the observation itself, a fixed horizon, unchanging from one year to the next. Let priests notice small shifts in timing that an observer moving between different vantage points might easily have missed. Sopdet's rise became so significant to Egyptian religious life that it was personified as a goddess in her own right, closely associated with Isis, and celebrated as marking the start of the new year, a moment worth ritual observance rather than simple calendrical bookkeeping. The timing coincidence at the heart of this system was, from a modern astronomical perspective, exactly that, a coincidence, not a causal relationship. Sirius's heliacal rising is governed entirely by Earth's orbital position relative to the star, a mechanism with no physical connection whatsoever to monsoon rainfall patterns over the Ethiopian highlands thousands of kilometers away. The two events lined up reliably only because both are ultimately driven by the same underlying clock, the Earth's annual orbit around the sun, which controls both the apparent motion of stars through the year and the seasonal shift of monsoon rain belts across the planet. Egyptian priests had, without any theoretical understanding of orbital mechanics or atmospheric circulation, identified a genuinely reliable predictive proxy for an event they could not observe directly, purely through patient, repeated correlation. Arguably one of the earliest large-scale examples in human history of predicting a natural phenomenon, accurately using a variable that had no direct causal link to it at all. A calendar built on a star, that single astronomical event ended up shaping the entire structure of Egyptian timekeeping. The Egyptian civil calendar divided the year into 12 months of 30 days each, plus 5 additional days added at year's end to bring the total to 365. A length matching the visible solar year, closely enough for most practical purposes. What the calendar lacked was any leap year mechanism to account for the roughly quarter day of extra length in the actual solar year, which meant the civil calendar drifted slowly out of sync with the seasons it was originally built to track, sliding backward by about 1 day every 4 years. Over a long enough span, that drift became substantial. Egyptologists calculate that Sopdet's heliacal rising and the civil new year, initially aligned, would drift completely out of sync and then realign again only once every 1,460 years. A span now called the Sothic cycle. For most of Egyptian history, this meant the civil calendar's stated new year, and the astronomical event that had originally defined it slowly separated, sometimes by months, forcing farmers and priests to rely on Sopdet's actual observed rising, rather than whatever date the drifting civil calendar claimed, for any decision that genuinely depended on the flood's real timing. The calendar was, in effect, a beautifully engineered system, slowly working itself loose from the star that had inspired it. A flaw ancient Egyptian astronomers understood clearly, but apparently never felt compelled to correct with a leap year rule of their own. The 5 epigomenal days added to close out each year carried their own mythology, entirely separate from Sopdet. According to Egyptian tradition, the sky goddess Nut had been cursed by the sun god Ra to bear no children during any of the 360 days of the standard year, until the god Thoth, gambling against the moon and winning a portion of its light, used those winnings to create 5 additional days outside Ra's original curse. Nut used them to give birth to Osiris, Horus the Elder, Set, Isis, and Nephthys, one god born on each of the 5 extra days, embedding the calendar's own technical patch, itself a workaround for the imprecision of a 360-day year, directly into the origin story of Egypt's most important family of deities. The Sothic cycle's full 460-year span was long enough that no single Egyptian dynasty, and likely no single institutional memory within any one temple, ever directly observed a complete realignment from start to finish, which means the cycle functioned more as a calculated astronomical fact, something priest-scribes could derive mathematically from known drift rates, than as a phenomenon anyone alive at the time could have personally witnessed beginning and ending. What they couldn't explain. Predicting when the flood would arrive was one problem Egyptian astronomy solved convincingly. Explaining why it happened at all was a different matter entirely. And on that question, Egyptian religion offered myth rather than mechanism. The god most directly associated with the inundation, Hapi, was depicted as an androgynous figure with a swollen belly and pendulous breasts, symbols of abundance and fertility. And one strand of religious tradition held that the flood itself originated from Hapi's tears of joy, an outpouring of divine emotion made physical. A separate and equally prominent tradition tied the flood instead to Isis, weeping for her murdered husband Osiris, her grief manifesting as the rising water that annually renewed the land, in the same way Osiris himself was believed to be renewed each year in the afterlife. Both explanations tied the flood to Egypt's core religious narrative about death, renewal, and cyclical rebirth, which suited Egyptian theology perfectly. Neither one offered anything resembling a physical mechanism, and Egyptian priests, for all their careful astronomical record-keeping elsewhere, never appear to have treated that gap as a problem requiring further investigation. Surviving religious poetry captures how central that unexplained gratitude was to Egyptian civic life. The hymn to Hapi, known from Middle Kingdom papyri, addresses the flood god directly as the one who waters the meadows and makes every workshop rich. Praising an act of providence, the hymn never once attempts to explain mechanically, treating the flood's arrival as something owed to divine favor and correct ritual observance, rather than a natural process with an identifiable physical trigger anyone might investigate. A separate tradition located Hapi's dwelling in a cavern near the first cataract at Aswan, close to where the Nilometer at Elephantine would later be built, envisioning the god as physically releasing the flood's waters from an underground source at the border of Egypt proper. A belief that placed the perceived point of origin within Egyptian territory itself, even though the water's real source lay far beyond any border Egyptian priests ever mapped or visited. Measuring what they could not predict precisely. Knowing when the flood would begin still left an entirely separate question unanswered. How high would it actually rise? Sopdet's heliacal rising gave Egyptian officials a reliable date. It gave them no information whatsoever about volume. And volume was what actually determined whether a given year brought prosperity, hardship, or disaster. For that, Egypt relied on a genuine physical instrument, the Nilometer, typically built as either a graduated column standing in the water or, more elaborately, a stone staircase descending into the river with measurement marks cut directly into the walls. The best preserved ancient example survives on the island of Elephantine at Aswan, a stairway of over 50 steps leading down to the water's edge, marked in cubits. Egypt's standard unit of roughly 52 centimeters, further subdivided into palms and fingers for finer readings. These readings carried direct financial consequences. Egyptian administrators calibrated tax rates to the Nilometer's measurement each season. A flood reaching the ideal mark, traditionally cited as around 16 cubits at Aswan, produced a standard tax assessment. A higher or lower reading adjusted rates accordingly, sometimes waiving taxes altogether in a genuinely poor year. The Nilometer, in other words, was the one piece of Egyptian flood monitoring technology that actually qualifies as an instrument in the modern sense. A calibrated measuring device producing a specific numerical reading. And it existed precisely because the star that predicted the flood's timing had nothing to say about its severity. Officials responsible for reading and recording Nilometer levels held their own recognized administrative role within the Egyptian bureaucracy. Their measurements feeding directly into tax assessments, handled separately by scribes and treasury officials further up the chain. A division of labor between astronomical prediction, physical measurement, and fiscal administration that reflects a surprisingly modern separation of function for a system built without any centralized scientific institution behind it. The tradition proved durable well beyond the pharaonic period. A Nilometer still stands on Rhoda Island in Cairo. Built in 861 CE under the Abbasid Caliph al-Mutawakkil and overseen by the astronomer al-Farghani. Its graduated column marked in 19 cubits, essentially the same cubit-based measuring principle Egyptian officials had relied on more than 3,000 years earlier. Adapted with only minor refinement across multiple religions, languages, and ruling dynasties, Nilometers were never confined to a single site. Beyond Elephantine, ancient sources and archaeological surveys place additional measuring stations at Memphis and at various points along the delta, allowing officials to track the flood's progress as it moved downstream and cross-check readings from one location against another. A discrepancy between an upstream and downstream reading could itself carry useful information. An early warning that the flood was arriving unusually fast, unusually slow, or unevenly distributed across the kingdom's different agricultural regions. Refinements that turned a single measuring stick into something closer to a distributed monitoring network spanning the length of settled Egypt. That network's records, when they survive at all, offer modern historians one of the only continuous, quantified data sets from the ancient world. A multi-century run of flood height measurements that climate researchers still consult today when reconstructing the Nile's historical hydrology, making a bureaucratic tax assessment tool into an inadvertent scientific archive spanning far longer than any deliberately designed modern monitoring program has yet run. When the prediction held, but the flood failed. The starkest surviving account of what happened when the Nile's flood underdelivered comes from the famine stela, a granite inscription on Sahel Island near Aswan, describing a catastrophic 7-year run of low floods, framed as occurring during the reign of the 3rd dynasty pharaoh Djoser. According to the inscription, Djoser, desperate over a famine severe enough to drive Egyptians to abandon their homes and their children, appealed to the god Khnum, guardian of the Nile's source at the first cataract, and received a promise in a dream that the flood would return once Djoser built Khnum a proper temple. Modern epigraphic analysis dates the stela's actual carving to the Ptolemaic period, roughly 2,000 years after Djoser's reign, which makes it a retrospective religious composition rather than a contemporary Old Kingdom record, almost certainly commissioned by Ptolemaic-era priests at Khnum's temple, partly to reinforce their own institution's claim to controlling the flood's favor. Whatever its true date of composition, the anxiety underlying the famine stela was entirely real and recurring throughout Egyptian history. Sopdet's rising told Egyptian farmers, with real precision, exactly when to expect the water. It offered no guarantee whatsoever about how much water was coming. And years when the flood ran low, regardless of how accurately its arrival had been predicted, could still produce exactly the kind of prolonged agricultural collapse the stela describes. A reminder that timing and abundance were two entirely separate problems Egyptian civilization never fully solved together. Some modern climate historians have proposed that a genuine cluster of low Nile floods around 2200 BCE contributed to the political fragmentation that ended the Old Kingdom and ushered in the First Intermediate Period, pointing to inscriptions in which provincial governors of the era claimed credit for feeding their districts during years of hardship. Though the precise weight of climate against administrative and succession problems in that collapse remains genuinely debated among historians rather than settled fact. The famine. Stela itself is unusually specific about the toll a failed flood took on ordinary life, describing granaries emptied, temples closed for lack of offerings, and people reduced to what the text calls robbing each other out of desperation. A level of narrative detail that, regardless of when it was actually carved, reflects a society that understood exactly what was at stake when the one variable Sopdet could never predict, volume rather than timing, failed to cooperate. The answer, Egypt never found. Egyptian floods varied so dramatically in severity from year to year for a reason that had nothing to do with anything happening inside Egypt itself. And no ancient Egyptian source ever correctly identified it. The Nile's flood originates almost entirely outside Egypt's borders, in the monsoon rains that strike the Ethiopian highlands each summer, feeding the Blue Nile and the Atbara River with a volume of water that dwarfs the White Nile's more modest, consistent flow from equatorial Africa. When Ethiopian rainfall ran heavy, Egypt's flood ran high. When it ran light, the Nile at Aswan fell short, regardless of how precisely Sopdet had risen on schedule that June. Egyptians, whose southern knowledge of the river's course extended only a limited distance past the first and second cataracts, had no way to observe the actual source of the variation. since it was unfolding in mountains they never visited. Generated by a weather system, the Indian Ocean monsoon, whose existence they had no reason to suspect. Herodotus tried and failed to get an answer out of the Egyptians themselves. Writing in the 5th century BCE, he recorded that despite direct questioning of priests and local informants, he could learn nothing at all about what made the Nile behave in a manner opposite to every other river he knew of. Rising in summer rather than winter, a reversal that struck Greek observers as strange precisely because most rivers familiar to them, fed by winter rain and spring snowmelt, ran highest in the colder months and lowest in summer, the exact opposite of what the Nile did every single year without exception. He records several competing Greek theories current in his own time. That the flood came from strong seasonal winds, from the ocean, from distant melting snow, and dismisses each in turn without ever landing on the correct explanation himself. Centuries later, the Roman Emperor Nero reportedly sent an exploratory expedition south, specifically to trace the Nile to its origin, only for the party to report back that they had been stopped by the Sud, a vast, near-impenetrable swamp of floating vegetation in modern South Sudan that still frustrates river navigation today. An obstacle that kept the river's true source hidden from organized state-sponsored investigation for nearly 2,000 additional years, after Herodotus first tried and failed to get an answer from the Egyptians themselves. The true cause remained genuinely unresolved, not just in Egyptian tradition, but in the wider ancient and medieval world. Until 19th century European explorers finally traced the Blue Nile back to its source at Lake Tana in the Ethiopian highlands, and connected its seasonal monsoon-fed surge directly to the Nile flood downstream, closing a gap in human knowledge that had stood, remarkably, for the entire span of Egyptian civilization and every empire that followed it. Scottish explorer James Bruce claimed to have reached the source of the Blue Nile at Lake Tana in 1770, though later verification and more precise mapping of the river's full hydrological system continued well into the following century, refining rather than overturning the basic monsoon-driven explanation that finally answered the question no Egyptian priest, however carefully he tracked Sopdet's rising, had ever been in a position to answer himself. Legacy. The cycle. Egyptian priests tracked by starlight for 3,000 years ended, finally and permanently, in 1970, when the completed Aswan High Dam sealed off the Nile's annual flood entirely, replacing it with a regulated, dam-controlled water release that no longer depends on Ethiopian rainfall, reaching Egypt on any particular schedule. The dam brought real, measurable benefits, protecting against both catastrophic floods and devastating low-water years of the kind described on the famine stela. And it converted the unpredictability that once justified an entire religious and astronomical tradition into a matter of engineered water management instead. Sopdet still rises heliacally every summer, exactly as it did for the priests at Heliopolis, visible to anyone in Aswan willing to watch the eastern horizon before dawn. Its timing calculable today by modern astronomers to a precision no ancient observer could have matched. Even though the event it once foretold no longer happens downstream at all, it no longer predicts anything, because there is nothing left for it to predict. The star kept its ancient appointment. The river, for the first time in 5,000 years of recorded human presence along its banks, did not keep its half of the bargain. Not because the monsoon in the Ethiopian highlands ever stopped, but because modern engineering finally intervened between that distant rainfall and the answer Egyptian farmers used to wait for every June. Egypt's dependence on water originating far beyond its own borders. The same vulnerability that once left Herodotus unable to get a straight answer from anyone has resurfaced in the 21st century in a strikingly literal way. Ethiopia's construction of the Grand Ethiopian Renaissance Dam on the Blue Nile, completed over the following decades, has drawn sustained objection from Egyptian officials concerned about downstream water security. A modern geopolitical dispute unfolding over precisely the same stretch of highland river system whose seasonal rains once decided, invisibly and without explanation, whether an Egyptian farmer 3,000 years ago would eat that winter or starve.